Back at it. More 4.1 max and minimum values. Doing a little bit of algebra review. This will be our video 2. Can you even read that? I don't know. So we're going to just talk more about the idea of our absolute max and mins, our local max and mins, because local max and mins are going to be the big thing we deal with later. This first section, there's going to be a game called the closed interval method. That will be the game we play the most. That's the good testable shit. But we're going to continue our exploration throughout algebra with our maxes and our mins, locals, and absolutes. So we've gone through, we had our definitions. If you've forgotten them, there we are. We played a little game with that, and now we're down to, let's see some more max and mins. So we've created two different, two graphs are sitting here. So let's look at the one on the left. Now let's talk about, actually let's do first our absolutes. Let's talk about an absolute max. So where's our absolute max on this? And right below, this is actually just y equals x squared, kind of stretched out a little bit. Y equals x squared, there's some arrows continuing off. So this is saying it goes on forever. Therefore, you can't have a value that's larger than every other value of x, just by definition. You can't have some value of c right here that is bigger than all other x's if that shit's taken off to infinity. That's impossible. It's not going to work. So absolute max? Nope. And shit, if there's no absolute max on here, well, we're looking, and we're like, well, what about a local max? But there's no peaks. We want to think with locals, think peaks and valleys. There is an exception to the rule. You'll see it in your homework. Holes and stuff that won't naturally happen. I'm not even going to talk about that shit. Maybe just find it in your homework. You can see the exception to that rule. But local maxes, I don't see any frickin' peaks. I'm saying let's get the hell out of here. Now let's go back to our absolute min. Well, shit, there is definitely an absolute min. It's right down here, huh? The location, its address is 0. Well, and it is 0. So we can have that f of 0 equals 0 is our absolute min. It's the smallest point on the entire graph. But at the same frickin' time, it's also the local min. It's the only valley that we have. So while we have both that, we also have this. That is the absolute min and the local min. They happen to share the same point. Cool. So we handled the one on the left, our y equals x squared. And now we move to the one on the right. Oops. We take a look at the one on the right, and let's start again with our absolute max. Once again, we're not going to have an absolute max, because this is going to take off and go up to infinity. And let's zoom in on this sucker so you can see some stuff that's going on with it. So since that's taken off, we have asymptotes, and oh my gosh, there's so much stuff going on. There's not going to be an absolute max because of these frickin' arrows right here. The fact that it's going up forever, that will tell you for certainty that we do not have an absolute max. The same thing can be said if we're going to be taken off and going down to negative infinity. That means we can't have an absolute min. We can't find a value that's going to be smaller than all other values of x. So we don't have an absolute min as well. So now we're only stuck with looking for a local max or min. Now this might be a little bit rough. So fortunately, from this little Desmos thing that popped out, these little points, if you look in here, these are either going to represent our, here's our intercepts. And then what's dope about Desmos is it'll give you right here, and it'll tell you your peaks and your valleys. Gives you these little points. So if you graph something up in Desmos yourself, check that out. Super helpful. Super helpful. It's also ways and tricks for you to be able to figure out when derivatives equal 0, but I'm getting ahead of myself a little bit. So when we look at this, we're like, well, let's see if we can't find a local max. See if we can't find one. So we'd have to be at some sort of peak. Now it'd be hard to see, but fortunately Desmos hooked it up that there's actually a little bit of a peak right here. That's a peak. It doesn't look like it, but that's taken off towards some sort of horizontal asymptote where it's getting closer and closer to 0. So it peaked right there, and I think that value was 3 right below it. Oops. Come on, technology, come back to me. There we go. There we go. So we can now say that our local max is going to be at f of 3. I'm not exactly certain what that height is. We figured out. But then we also have a local min, right? The only other place where we might have a valley. There's a valley right there. There's our valley. Nowhere else does it peak. When we look off to the left of this graph, see up here, we're heading this direction. It never hits some big value. It just keeps increasing and getting closer and closer and closer. Think about me walking towards the wall with that limit idea. So the only spot we're going to hit a min is just going to be right there. And we're going to say that that is at f of 1. We found ourselves a local min. Well, let's do one more. Let's keep looking. Let's continue this exploration of algebra. But again, we want to be thinking local mins, local maxes. That's going to be, again, we'll start taking derivatives, set them equal to 0, and we'll be able to solve for those later. So let's look at one more. I drew up a beautiful graph, right? Hey, it's y equals sine of x, or, oh, I'm sorry, f of x equals sine of x. Well, here, we're going to have quite a few things. Since everything's trapped between -1 and 1, sorry, my graphs are not the greatest, but we can say that we have a max, it's a max, right? All those points are maxes. They're both local and absolutes because they're peaks, yet they're also the highest place on the entire graph, highest height, you know what I mean? The height. So we can say here that both are local, and there goes my dogs. Thank you, puppies. So that local and the absolute max being the same thing. We're going to say that this is at f of, well, shit, which one? Oh, crap. This might be kind of tough. So maybe we could say at x equals, and see if we can't find some sort of pattern that's going on, because this one repeats so many times. It looks like we have one at pi over 2, 5 pi over 2, -3 pi over 2. And I'm curious, many of you all know how often a trig function repeats for sine and cosine. I mean, tangent's different, but I'm pretty sure that's every 2 pi. So what we could say here is that we have pi over 2 plus some 2 pi k, for k the element of any integer. So k is some number like negative, positive, 1, 4, 7, anything like that, zeros included. And now we could write down that our local and our absolute min, and let's write out where they'll be at x is equal to, and where are those suckers? Let's see if we can't find those. -5 pi over 2, -pi over 2, 3 pi over 2, 7 pi over 2. But once again, all those gaps right there are off by 2 pi. So just choose a value. Like I like -pi over 2. Let's just start there. And we're going to say that x is equal to -pi over 2 plus some 2 pi k. And again, k is the element of the integers. So now we found our absolute mins and maxes, and they just happen to be the same freaking things. This happens with sine waves and cosine waves, things of that manner. So hopefully you're starting to really get what a local and an absolute max and a min are. And we will see you in the next one, where we're going to learn a little bit about the extreme value theorem.